Hello, Chem 1110 students. Today we're going to start talking about Chapter 8, which is all about chemical reactions. And this first part is going to be talking about what a chemical reaction is. And so what a chemical reaction is basically a kind of sentence or equation that describes chemical changes. It shows how atoms rearrange after they collide. It tells us, for instance, what the reactants are, what are the things that are colliding, and we put those on the left side of an arrow. These tell us what molecules are colliding, and then on the right-hand side of the arrow, we put the products in chemical formula, and the ratio, we have to balance these equations so that we don't lose any material, and that ratio tells us how many of each kind of atom you need to make the product that you get. The other thing that we'll usually include in a reaction equation are the physical states of the materials, because that can have a lot to do with how the reaction goes. All right, so the first thing we have to do with a chemical reaction is we have to balance it. This means that we have the same number of atoms on the left side as on the right side, because the equation has to obey the law of conservation of mass. Our reaction cannot make any new material nor lose any material that was originally there. So if we look at the reaction of the production of water from hydrogen gas and oxygen gas, we can tell what the species are from this, but we can see it is not balanced because we only have one oxygen on the right-hand side and two on the left-hand side. And so what we can do is put stoichiometric coefficients or numbers to the left of the chemical formulas to tell us how many of those molecules have to react together. And so in this case, we would say there's two diatomic hydrogens reacting with one diatomic oxygen, and that would produce two water molecules that are in the liquid state. Okay, so the question is how to balance a chemical equation. You need to realize this is generally a trial and error kind of thing, but there are some standard steps you can do that will facilitate the process. One thing is always think about the compounds before you change the coefficients on elements, because elements are very easy to change. Leave them till the end. If you have polyatomic ions, you generally want to leave them as a unit. So you wouldn't take sulfate and break it up into the sulfur and the oxygens. You would count it as a sulfate unit. And then the other thing is you want to keep track of all those numbers. And if you change a coefficient, you have to change the number of atoms that you have. And I have a couple of examples here for you. The other thing I did mention before is you need to know the physical state. And so in this reaction of ammonia gas with HCl gas, you get a salt. It's a solid, and so that's pretty important to know. Whereas the second reaction is the production of sulfuric acid, and you do it by bubbling SO3 gas through water. So those states of matter are very important. All right, so now we're to the examples I had for you. And so we have a reaction here that is obviously not balanced. There are two gold atoms on the left side, only one on the right side. And so we need to go in and balance this. And the way I like to do it is to make a list of the atoms or the kinds of elements that exist. So I've got gold, sulfur, and hydrogen just listed under the reaction equation. Then I go through and I count how many are there in this original equation. So there's two golds on the left, only one gold on the right, three sulfurs on the left, only one sulfur on the right, so on and so forth. And now I'm going to go in and put those coefficients in front of these molecules in order to balance my number of elements, of the atoms of each element. So I'm going to start with that H2S, hydrogen sulfide. because it's a compound. So I want to start with it. So I put a 3 in front of it. That says I have 3 H2S molecules. So now I have 6 hydrogens on the right and 3 sulfurs. And you note I cross out the original number I had because I've changed it now with a coefficient. And I have managed to balance my sulfurs, but I've kind of screwed up my hydrogens. So I'm going to do my hydrogens by putting a coefficient in front of the diatomic hydrogen on the left. I put a 3 there, and now that gives me 6 hydrogens on each side. I have 3 sulfurs on each side. So the only thing that's not balanced is the gold. It's shown as an element on the right side, so it's pretty easy to just put a coefficient of 2 in front of it, and now I have a balanced equation. All right, another example looks very simple. This is iron 2 oxide reacting with oxygen and producing Fe2O3, which is rust. And so this is what happens as things rust outside and they react with the oxygen in the air. So I start out writing down the elements in the equation. And so I have iron and I have oxygen. And then I count how many I have on each side. So I have 1 iron on the left, 2 on the right, 3 oxygens on the left because I have O2 and then there's an oxygen in the iron 2 oxide. I have 3 oxygens on the right. So my oxygens are already balanced, but I need to balance the iron. And so when I put a coefficient in front of the iron 2 oxide, it's going to really mess things up. Again, my irons all balanced, but now I have 2 oxygens from those 2 molecules plus the O2, so now I have 4 oxygens versus the 3 on the other side. The simple way to balance that would be to put a coefficient of 1/2 in front of the O2. And now I have 3 oxygens on the left, 3 on the right. Everything's balanced, but I have a fractional coefficient, which is not generally something people want. And so I can get rid of it by multiplying everything by 2. And so when I do that, it removes the fraction, and now I have 4 FeO plus my O2 gives me 2 Fe2O3, and I go through and I count my atoms. I see I have 4 irons on both sides, and I have 4 plus 2, 6 oxygens on the left and 6 oxygens on the right. So this process will generally help you balance an equation, but we call this by inspection. These are not oxidation reduction reactions. There is no transfer of electrons. We'll get to those later. All right, so now we're going to talk about the different kinds of reactions there are. In this book, we talk about 3 in particular: combination, decomposition, and combustion. In the homework, we often will talk about double replacement, single displacement. So there's different ways to classify them, and we'll talk about more of those as we go along. So a combination reaction is exactly what it sounds like. It takes 2 things and combines them to form one new product, a single product. And this is our ammonia and HCl reaction. A decomposition takes a single reactant and breaks it into 2 or more products, as this calcium carbonate reaction. And the little triangle over the area says we are heating this material to get the CO2 off. And then the final one is combustion. And so combustion is burning, and it's particularly the burning of a compound that has carbon and hydrogen and maybe oxygen in it. And it always produces CO2 gas and liquid water, as with this example here below. All right, so I have a couple of, 3 reactions here. We want to say what type they are. So that very first one, we take 2 reactants, we get a single product. So that's a combustion reaction, combination reaction. It's also called a synthesis because you're making something new. The next one, we have a material that contains carbon, hydrogen, and oxygen. We react it with oxygen and we get CO2 and water. So that's a combustion reaction. We always suspect that when we see our products are CO2 and water. And the third one was potassium chlorate, which we are actually heating, although we didn't show the triangle here. And this decomposes into potassium chloride and oxygen gas. And we used to use this reaction quite often when we were trying to produce a gas or if we needed oxygen for a reaction. So that's a decomposition reaction because we're just taking one thing and breaking it apart into its two pieces. All right, so we will move on to part 1B next.